This is lecture 30 on urban transportation planning. The discussion on route assignment will be continued and completed in this class. You may recall in the previous class at the end we tried to list the different techniques available for route assignment. We know now there are 3 techniques available for route assignment. They are: number 1, all or nothing assignment technique; number 2, multipath assignment technique; and number 3, capacity restraint assignment technique. And we have also seen a numerical example to understand all or nothing assignment technique, isn't it? To look at the principle involved in all or nothing assignment technique, you can just follow the 3 steps illustrated here. Step 1 is just to find shortest route between the TAZs. TAZ is nothing but traffic analysis zone or simply traffic zones. Step 1 is finding the shortest route between traffic analysis zones, because our interest of movement or mobility is between zone centroids. So, find out the shortest path between the centers of traffic analysis zones. Step 2, assign all trips to links comprising shortest route, right, and nothing to other routes, right. That is why it is all or nothing assignment technique. Assign all trips to links comprising shortest route, represented in the form of minimum path tree, isn't it? And step 3, continue until trips between all traffic analysis zone pairs have been assigned. Continue the process until you cover all the zonal pairs, isn't it? This is a simple, inexpensive and fast method of route assignment, because we just develop minimum path tree and assign the whole of the traffic to the minimum path. That is how it is very fast and simple. This method depicts the routes most travelers would use in the absence of capacity and congestion effects. Basically, we assume that there are no problems related to capacity of any link or congestion developed on any particular link. We assume uncongested free flow condition on all the links. Based on that assumption, we assign traffic on all the links comprising the minimum path, isn't it? Results of this method are easy to understand and interpret. Interpretation is quite simple and understanding is also relatively easier. Despite these advantages, this method has got one serious problem. The disadvantage of this method is that it generates unrealistic flow, unrealistic traffic assignment in situations where there are minor differences in travel impedance between alternative routes. Let us say we have 2 alternative routes between zones 1 and 2. If the travel time between, or if the travel time along route 1 is 11 minutes for example, and the travel time along route 2 11.5 minutes. So, the difference is minor. In practice, these differences do not matter much. People might use either route 1 or route 2, but as per the algorithm that we use for all or nothing assignment technique, the whole of the traffic will be assigned to route 1, which has got a travel time of just 11 minutes, leaving the other alternative route which has a travel time of 11.5 minutes empty, which is not realistic. So, that is the problem with this type of assignment. Clear? The second method of assignment is multipath assignment. As the name implies, this technique assigns traffic on multiple paths, right. In essence, of course, the all or nothing assignment assumes that all trip makers traveling between a specific pair of zones actually select the same path. That is a basic assumption. There is no alternative path as far as the previous technique is concerned. In reality, however, interchange volumes are divided among a number of alternative paths. So, that real aspect or reality is captured in multipath assignment technique. Algorithms that are capable of determining several paths between each pair of zones in order of increasing impedance are available. So, we need to have some algorithm to assign traffic in some order. We cannot equally divide the traffic among the alternatives. The choice of route will depend on the travel time implication. Less is the travel time, more is the likely traffic that might use a shorter route compared to a relatively longer route. So, we need to have some kind of algorithm to apportion the traffic among various alternative routes. Therefore, it is possible to apportion the interchange volume between these paths according to some realistic rule. Can anyone think of some rule to apportion traffic among alternative paths with different travel times? 10 minutes, 11 minutes, 12 minutes, like that. Let us say 3 alternatives. How to apportion the traffic? But one reality is that 12 minutes path will have relatively lesser traffic compared to the 10 minutes path, is not it, because a 10 minutes path is shorter compared to 12 minutes path. Shall we say that the traffic taking different routes might be directly proportional to the inverse of the travel times, inverse of travel times, right. That is one suggestion given. Irvine and Von Cube suggested the following inverse proportion function to compute the fraction to be assigned to each of a number of interzonal routes. This is the formula suggested by Irvine and Von Cube. PR is equal to Wijr raised to power minus 1 whole divided by sigma x equal to 1 to n Wij x raised to power minus 1. Wijr here is the impedance of route R from I to j, or for travel from I to j, right. PR is nothing but the proportion of trip assigned to route R. Clear? You can see the same information here. The inverse of travel impedance of the concerned route is taken in the numerator, and the sum of the inverse of the impedances of all the routes are taken in the denominator, is not it? Let us take a small numerical example and try to understand the multipath method of traffic assignment. This is the information related to a small network. Link designations are given in column 1. and travel time in minutes is given in column 2, and practical capacity of each link is also given to us as an additional information, even though it may not be very essential at this stage. So, you can see some numbers, node numbers used to designate the links, and the question is this: assign a traffic volume of 9000 PCU per hour between nodes 1 and 20 by multiple route assignment technique. We have to assign a traffic of 9000 PCU per hour for movement from node 1 to node 20, right. Since we have just node numbers and used to designate links, it will be convenient for us to make a sketch of the given information to understand the problem better. You sketch out the route network based on the information given in column 1, link information. If you do that, you will get this figure. The link designations you may recall: 1, 11, 11, 12, 12, 16, 16, 20, then 11, 15, 15, 18 and 18, 20. Our interest is to find out the travel time from 1 to 20 along the 2 alternative routes, and then assign traffic based on the algorithm. Clear? And what is the travel time along 1, 11, 12, 16, 20? Travel times are indicated with white colored numbers. Okay. So, 3 plus 2 5 plus 4 9 plus 2 11 minutes, and the travel time along the other alternative path, namely 1, 11, 15, 18 and 20 is equal to 3 plus 2 5 plus 3 8 plus 2 10 minutes. So, there are 2 alternative paths involving travel times of 10 minutes and 11 minutes. So, the paths are 1, 11, 15, 18, 20 involving a travel time of 10 minutes, and then 1, 11, 12, 16, 20 involving a travel time of 11 minutes. Simply use the algorithm and get the proportion of traffic to be assigned to the 2 alternative routes. As per the equation 1 that we have seen, the proportion using route 1 is 1 by 10, inverse of the travel time implication, divided by 1 by 10 plus 1 by 11, that is equal to 0.524, and the actual volume will be the traffic assigned to route 1 is 0.524 into the total traffic is 9000, and this works out to 4716 PCU per hour. That is the traffic volume assigned to route 1 with travel time of 10 minutes. And as per the same equation, the proportion using route 2 will be 1 by 11 divided by 1 by 10 plus 1 by 11, that is equal to 0.476, and the actual traffic volume is going to be 0.476 into 9000, that works out to 4284 PCU per hour. It is a very simple example, and in practice you may have more number of links involving each alternative route, and sometimes the number of alternative routes available also may be more than 2. Clear? All the links on both the routes have sufficient capacity to take the traffic. Why we are making this statement? Because link capacity is given to us as additional information. You would have seen the third column of the table, link capacity was given. Suppose the assigned traffic of 4000 plus, in this case, the earlier case slightly higher. If the assigned traffic is more than a link capacity on a particular route, then what to do? you are apportioning traffic along two alternative routes. Let us say in one alternative route, one of the links may not be able to take the assigned traffic volume. Let us say assigned volume in this case as shown here is 4284, and if the capacity of one of the links is only 3500 PCU per hour, what do you do under such condition? It is obvious that you can assign only 3500 PCU per hour along that alternative route, and the balance has to be pushed to the other alternative route, provided the other alternative is able to take this additional traffic. Clear? So, that is how in practice you must manage assignment along various alternative routes. If you are given the information about capacity constraint, then you should be very careful and check whether the capacity is exceeded. If capacity is exceeded, try to distribute the traffic to other alternative routes, right. And use of multinomial Logit model. How use of multinomial Logit model is relevant at this juncture? All of you are familiar that multinomial Logit model can be used for mode choice analysis. We have used the model for mode choice analysis, isn't it? And is it possible to use the model for route choice analysis? You may recall that I told you about the scope of application of the Logit model. Logit model can be applied for any choice situation where randomness is increased. It could be choice between 2-3 just consumable items or 2-3 modes of transportation or several alternative routes available for choice for making trips. Basically, it is a question of choosing a particular route, knowing the travel time implication or total travel impedance related to each of the alternative routes. So, we have a set of alternatives and we try to understand the way people choose a particular alternative, isn't it. So, that is how, instead of using the earlier equation that we have seen involving the inverse of the travel times, you can also use multinomial Logit model to explain route choice, to do route assignment. Why should we use multinomial Logit model, or what difference it is going to make compared to the earlier method? You may recall multinomial Logit model incorporates the randomness related to individuals in choice of a particular alternative among the set of alternatives available, isn't it. The random part is incorporated in the choice process when you use multinomial Logit model, right. And the choice of route also need not be strictly based on only travel time implication. In practice, people might look at the overall generalized cost implication or overall travel impedance related to each of the alternative routes. So, when they try to create a bundle of various utilities or disutilities related to each of the alternative routes, the randomness comes into the picture. It depends upon the way individuals look at utility or disutility of a particular alternative route. Clear? So, that is what happens in practice. So, that is a use of multinomial Logit model is also appropriate in route choice analysis. It is very simple. it is not going to be difficult because the basic model structure is familiar to you. And as the following example illustrates, the use of the multinomial Logit model with disutilities based on path impedances is another possibility. Let us take a small example. A multipath algorithm found the interzonal impedances in general, not travel time, total impedances of the 4 shorter paths. Why 4 shorter paths? See, the alternative should be comparable. There could be several alternative paths if you consider the entire road network, right. You can go to the next station by travelling around a circuitous route, it is also possible, right. So, that cannot be reasonably considered as an alternative route. Alternative should be reasonably real alternatives. There should be basically shorter paths. Okay. That is where you need to understand the reason for putting the word shorter here between a pair of zones to be 1, 1.5, 2 and 3 units of disutility. Okay. Just units, it is not travel time. The bundle together is given some number as 1, 1.5, 2 and 3 units of disutility. Clear? So, you can name it as travel impedance, the total travel impedance along each of the alternative routes. Now, the problem is this: estimate the percentage of trips to be assigned to each of the 4 routes according to the MNL model, multinomial Logit model, right. The MNL model structure is given here. It is the same structure as we have seen earlier. The only difference is a symbol beta is introduced here. This is nothing different. This is just to indicate that the utility function Vj involves estimation of the parameters of the involved variables. Okay. It is an indicator, otherwise it has got no different meaning compared to what we have seen earlier. Where Pj is the probability of choice of alternative j and beta is the parameter to be estimated for the utility function, which is obvious, and m is the number of alternative modes including j, right. That clear? Now, applying this equation with the negative of the path disutilities. Disutilities are given as some numbers 1, 1.5 etc., and we must take negative of those values for application in the model, right, e power minus of something. In place of the utility terms, we obtain these results. I am just giving you the probabilities directly because it is simple substitution of the numbers in the equation. Probability of choice of route 1 is 0.47, probability of choice of route 2 is 0.29 and route 3 0.17, route 4 0.07. It is in the descending order. You may remember the corresponding disutilities associated with route 1, 2, 3 and 4. It was 1, 1.5, 2 and 3, is not it. So, when the disutility increases, we find that the probability of choice decreases. Okay. We simply substitute those numbers in the previous equation. The computational complexity of these models should not escape the reader's attention. Of course, computationally this is little complex compared to the previous thing where we simply considered inverse of the travel times, right. But computerized algorithms that deal effectively with this repeated nature of calculations are available, so nothing to worry. Okay. Whatever may be the complexity associated with analytical process can be managed with available computer program packages, right. Then the third method of route assignment, namely capacity restrained traffic assignment, right. and this is a basic concept to be kept in mind in reality. As the road traffic flow increased towards capacity, the average stream speed decreases from the free flow speed to the speed at maximum flow, right. It changes from UF to UM, M standing for maximum flow. Beyond this point, the internal friction between vehicles in the stream becomes severe because of reduced headway, right. The traffic conditions worsen to give you a level of service of E or F, which is the lowest, right, and severe shock waves and slow moving platoons develop when the traffic flow increases to reach capacity level, right. And it is to be noted that the interzonal flows are assigned to the minimum paths computed on the basis of free flow link impedances, usually travel times. So, whatever travel times we have been talking about so far are free flow travel times. But in practice, when you think of taking different alternative routes during morning peak hour, you do not perceive only the free flow travel time, you simultaneously perceive the possible traffic condition at that point of time along each alternative routes, and then involved travel time under that traffic condition, is not it. That is how we perceive the possibility of taking an alternative route when we try to take a decision in practice. So, unless this aspect is taken care of, our route assignment may not be that realistic. But if the link flows were at the levels dictated by the assignment during the assignment process, the link speeds would be lower and the link travel times, that is impedances, would be higher than those corresponding to free flow conditions. This implies that travel times in practice may not be equal to free flow travel time that we normally consider for assignment under all or nothing assignment technique or multipath assignment technique. As a result, the minimum paths computed prior to trip assignment may not be the minimum paths after the trips are assigned. You just consider a zonal pair, identify the minimum path tree, assign traffic, let us say based on all or nothing assignment technique. Once you assign traffic, a set of links are loaded with traffic volume, right. And when you take another zonal pair and assign traffic, some of the already loaded links will also come into the minimum path of the other pair also, it is likely. In that case, if you do not consider the effective traffic volume, existing traffic volume on the travel time, you will not be doing the exercise accurately, is not it. So, the point made here is, when you assign traffic in steps, you must realize that the travel time along the links increases. That increase should also be taken into account simultaneously while you are doing assignment, so that ultimately at the end of the process, the travel time that you take will be reflective of the reality. And for this purpose, several iterative assignment techniques address this particular convergence between link impedances assumed prior to assignment and the link impedances that are implied by the resulting link volumes, right. And these techniques are known as capacity restraint methods. There are minor variations, there are several approaches under capacity restraint technique. We just talk about the general principle implied or involved in capacity restraint method of traffic assignment, which basically involves consideration to the assigned traffic volumes while estimating the travel time and the resulting minimum path tree that employ capacity restraints. The relationship between link flow and link impedance is described as a link capacity function. The key to this process is the understanding of the relationship between link flow or link volume and link speed, right. So, when you assign some traffic flow onto a link, subsequently the speed is going to be less and the involved travel time is going to be more. So, you should know what is the relationship between traffic volume and traffic speed. If you assign say traffic volume to an extent of 20% of capacity of a link, what will be the extent of reduction of speed from free flow speed? That question has to be answered if you want to effectively apply the capacity restraint method of traffic assignment. That is a prerequisite, right. And several such functions are found in the technical literature. Number of researchers have come out with some functions relating traffic volume and traffic speed. The functional form developed by BPR, Bureau of Public Roads, USA, is expressed mathematically as follows, which is more commonly used by different agencies as well as countries. So, this is the BPR equation, which is very simple. W is the impedance of a given link at flow Q, is not it. We are interested to know the impedance on a link at a given flow level, that is given here as W, and W bar is the free flow impedance of the link. Under free flow condition, we should know what is the impedance or travel time implication, that is given here as W bar, and Q is a link flow, the actual flow at any point of time, and Q max is a link's capacity, right. And you can see W is given in terms of W bar. W you are estimating in terms of a free flow impedance, W bar multiplied by some factor. And if you look at the factor or multiplying part of it, you get some numbers as 0.15 and an exponent 4. These numbers are the result of calibration of this equation based on field observed data in the United States obviously. So, we can call this equation as an empirical equation which relates the travel impedance on a link at a given volume, traffic volume, to the free flow impedance condition, which is W bar, right. And this equation, when represented pictorially, gives you this kind of picture. This is how the travel impedance increases with increase in volume of traffic, right. And a free flow condition, as we have seen, the impedance is less, W bar only. As the volume increases to maximum capacity level, the impedance increases to 1.15 W bar, right. So, this function states obviously that at capacity the link impedance is 15% higher than the free flow impedance. Please remember, this is for the condition prevailing in the USA, but if you perceive the difference between free flow condition and capacity flow condition on Indian roads, the percentage is going to be less or more. what is the free flow speed for a motor vehicle, for car on urban roads in Indian cities, when you are allowed to drive freely as you desire, what speed you will maintain on urban roads? Still you cannot drive very fast blindly, you have to be careful, right. Maybe let us say the free flow speed is 70 kilometers per hour, right. And when the traffic is near capacity on the same road, can you imagine the speed that you will be able to maintain? Roughly about 20 kilometers per hour or even less than that. There will be a drastic reduction. So, obviously, this number is not going to be valid for Indian condition, right. That is to be remembered very carefully. So, we should not simply assume this, take this 15% very seriously and try to apply for the conditions prevailing here. Even in the US, there were some questions about these calibrated values, and subsequently they have made some changes. The original BPR capacity function was based on the relationships found in the 1965 highway capacity manual. The equation that we have seen pertains to the traffic condition, roadway and traffic condition that prevailed in 1960s. Since that time, the equation has been modified to be consistent with more recent data, right. One modification was to substitute parameters alpha and beta in place of the constant values of 0.15 and 4, and to allow these parameters to take different values, right, depending on facility type, design speed, the number of signals and other interruptions per mile, and few other roadway and traffic characteristics. Clear? And they have just given the values in a tabular form in the year 1985. Okay. In the 1985 edition of HCM, you find this information. They have classified the roads into two types, freeway and multi-lane roads. Freeways are roadways with unrestricted traffic flow condition, and multi-lane roads will have frequent interruptions for the traffic flow. Constrained traffic flow condition will prevail on multi-lane roads, and freeways will have unconstrained traffic flow condition, right. And even there the design speeds have been given three values: 50 miles per hour, 60 miles per hour and 70 miles per hour for both these two categories of roads, and the values of alpha and beta are given separately for each category, right. In general, you can find that the values of alpha compared to the corresponding values in the case of multi-lane roads are relatively more. Alpha is more in the case of multi-lane roads compared to freeways, and when you look at beta, it is less. Okay. This implies what? You can look back and look at the equation that you have seen and then try to perceive the difference, the effect of traffic volume and speed. Normally on inferior type of facility, the effect will be more significant compared to superior type of facility. That is the general understanding. That is what is meant by these relative changes in the alpha and beta values, right. And capacity restraint algorithm incorporate link capacity functions in their search for convergence to an equilibrium state. They may be either all or nothing or multipath. This statement is very important. I will repeat again. Capacity restraint algorithm incorporate link capacity functions in their search for convergence to an equilibrium state, right. That is the only part of this method. This is a component of the general method of route assignment. This capacitor restraint technique helps us to bring in a kind of equilibrium in traffic flow in the road network with due consideration to change in the travel time because of change in traffic volume due in the assignment process. But the actual assignment technique adopted will be again either all or nothing or multipath assignment only, right. Actually we follow only the first two basic methods of assignment. This capacitor restraint assignment is only part which enables better application of all or nothing or multipath assignment techniques, clear. An example of the former, that is all or nothing assignment technique, is an algorithm developed for Chicago area transportation study, CATS study, where the following assignment procedure is applied. Now we are going to see how to apply all or nothing assignment technique with incorporation of the principle of capacitor restraint, right. Now what we do to start with is this: an interchange is nothing but trips between a pair of zones is first considered, right, is chosen at random. You may have a large network, you can just choose any interchange, right. The minimum path is determined using the free flow impedances. First you build the minimum path tree taking free flow impedance as the basis first to start with, right, and the entire interchange volume, because it is all or nothing procedure, is assigned to this minimum path. You may have thousands of links and nodes. When you consider one interchange, one zonal pair, the number of links and nodes involved may be small, very small compared to the total number. In that case nothing wrong in just assigning or assuming free flow condition and assigning traffic. That is not going to be the end of it, it is only beginning, right. So that is what is being done as step 1. Then the impedances of the links that make up this path, this minimum path in step 1 are updated according to the assigned flows, and another interchange is randomly chosen for similar treatment. So after assigning traffic we change the impedances or travel times for all the involved links. Is it possible or not? We take one pair of traffic zones, right, and assign traffic from one zone to another. After identifying the minimum path tree, a set of links will be loaded with some traffic, right. Because we assign some traffic, for subsequent assignment on the same link, when we consider some other zonal pair, we need to know what will be the exact travel time. It will not be equal to the free flow travel time because we already have some traffic assigned on these links, is not it. So we must have some increased travel impedance, travel time would have increased for subsequent assignments, right. Since we have a relationship between traffic volume and speed, after having known the assigned traffic you can find out what will be the consequent or resultant speed on each of these links after the first stage of assignment, right. So knowing the speed you just find out the travel time implication and take that as the revised impedance for those links which were involved in the first step, right. So that is what is stated here. The impedances of the links that make up this path are updated, okay, according to the assigned flows obviously, right, and another interchange is randomly chosen for similar treatment. Then choose another zonal pair, assign traffic, after assignment update the travel impedance based on the assigned traffic volume. The procedure ends when all interchanges are considered. So, when you do this mechanically, you will find that simultaneously you are changing the travel impedance for concerned links, and this process will enable you to realistically assess the travel impedance and assign the traffic. Okay, this is what was done in CAD study. Although not realistically reproducing particular interchange flows, if you consider a specific zonal pair, it may not be very realistically interchanging, reflecting the actual interchange. The incremental updating of link impedances is expected to result in realistic estimates of the equilibrium in link flows. Ultimately, at the end of the exercise, you will find that there is some equilibrium maintained in the whole of the transport system network. That is the idea. Okay. Now, let us see how to go about doing the same exercise by multipath assignment technique or incorporating capacitor restraint in multipath assignment procedure. A multipath extension of the same CAD study begins with an uncongested network or network under free flow condition, finds all of the minimum paths and assigns a portion, say 20% of each interchange volume to these paths. Are you able to follow this statement? What we do is we consider all the zonal pairs to start with and identify the minimum path for zonal pair travel. That means the minimum path for any travel, for any movement from one zone centroid to another zone centroid for the whole of the urban area or whole of the road network is first determined, right. Minimum path for all cases is first found, then you just assign a portion of the total traffic volume between zonal pairs initially to start with. Do this for all the zonal pairs again. For example, you take 20% of the total traffic volume and do the assignment for all the zonal pairs covering the entire road network. That means the whole network will be loaded to an extent of 20%. Now, you revise the travel impedance based on the assigned traffic volume. Once you put 20% of traffic, your travel time is not going to remain the same, it is going to increase, and you have the relationship between traffic volume and traffic speed. So, get the speed for each of the links after assigning 20% of traffic and then work out the corresponding travel impedance in terms of travel time. So, that is the new travel time for you. Once you have changes in travel time, then you will find the minimum path trees also change. Again, before you start the next assignment process, you must determine the minimum path tree again for all the zonal pairs covering the whole of the network. Once you complete that, you assign another 20%, say for example, right. So, like that you do assignment in stages and complete the process covering the whole of the traffic volume, maybe in 2, 3 or 4 or 5 stages. Please remember, at every stage you have to work out new minimum path trees for zonal pairs before assigning subsequent traffic volume. It then updates the link impedances according to the resulting partial link flows, because we assign only some percentage, recomputes the minimum paths and assigns the next increment of the interchange volumes after recomputing the minimum paths. The procedure is continued, it continues until 100% of the interzonal flows are assigned. Clear? So, that is about the 3 methods of route assignment. All these discussions are relevant for assigning traffic when private or personal transport modes are used. Then how to assign traffic when the travelers use transit service? In the case of private transport modes, we easily convert person trips into equivalent vehicular trips and then just assign traffic in terms of number of vehicles. But in the case of transit, they are plying on fixed routes, and you cannot just convert the person trips into equivalent number of transit vehicles. Even from a traffic zone, if you convert all the person trips into equivalent vehicle trips, you may end up with say 1.5 wagons of train service. That is not the realistic way. There should be some other procedure to be followed for assigning transit trips. Transit trip assignment is different and more complex than highway trip assignment because of the following reasons. The first is this: the network of transit services is different from that of personal vehicles. That is one thing. Network is totally different. Links in this network include bus or rail service running between two stops or stations. The definition of links or nodes are not relevant for transit trips. As far as transit trips are concerned, say for example the transit service that you consider is a bus service. Each bus stop is a node, not the intersections. Okay? Each bus stop will be considered as a node in your transit network. Similarly, each railway station will be a node in your rail transit network. That is a major difference. Many of the public transit services share road links with private vehicles, right. So, their speeds will be changing from link to link. You cannot have a generalized free flow speed, etc. This complexity has to be tackled by some means. I am just listing the differences between transit assignment and previous case. Okay. The transit assignment involves the movement of passengers and not vehicles. So, we must consider only passengers to be moved using the available transit service. If there are 100 people taking bus during morning peak from a zone, you just push them into the available transit vehicles in batches, right. Let us say there are the frequency of bus service in 1 hour is about 5 on a particular route. Then divide this total number into 5 batches and push them into the buses. So, we are assigning only person trips as far as transit assignment is concerned. It is a major difference. Okay. The travel time has an in-vehicle component and out-of-vehicle time, such as waiting at stops and walking to and from stops and so on. So, when you think of travel time components, you should not just think of only in-vehicle travel time when you estimate travel times in the case of transit trips. And passengers may also transfer between two routes and even drive part of the way to board a public transit vehicle. Use a bicycle to go to railway station, park the bicycle and take the train, or use a motorized two-wheeler. So, it becomes a multi-mode transportation. So, all these effects are to be brought into your analysis process. I am just listing the complexities only. In private car networks, the monetary cost is directly associated to fuel consumption, tolls and parking fees. In transit services, the different fare structures determine the monetary cost associated with a trip. Okay. If you are including cost component in your travel resistance, then this difference has to be understood very clearly. Transfer cost and parking cost should also be included if an auto, maybe car, motorized two-wheeler is used to get to the transit station, as I mentioned earlier. So, these are the differences between transit assignment and route assignment in the case of personal transport vehicles. For some OD pads, there may be sections in the path where more than one parallel service is available. Let us say the travel distance or travel time implication is 50 minutes. For first 10 minutes, the person may have only one transit service available, and later on for next 30 minutes of travel, there may be train service as well as bus service available in parallel. Some might switch over to the other transit mode because it is some way more convenient or comfortable compared to the other one. So, this kind of changes, availability of more choices should also be taken into account when you assign traffic. This parallel service allows a passenger to select a preferred service to travel over that particular section. This choice can be complex and requires a detailed assignment methodology to be followed. That is about the complexities related to the transit assignment. Now, look at the master flow chart and find out where we are. We are almost at the box, last but one box on the left hand side. The final step is check against measured volumes. Once we assign traffic, it is possible for us to actually check the traffic volume link by link, because we theoretically assign traffic and create traffic volume. You can actually measure the same traffic in the field, and it is possible for us to compare the field observed traffic volume with your assigned traffic volume. That is the method of checking the correctness of your result. There is no distinct calibration procedure for assignment models, please understand. It is only comparison of the actual field observed data with your result that you get through the assignment process. Clear? Compare both, and if they are matching satisfactorily, you stop. Otherwise, there is something wrong somewhere and you go backwards and check every step, each of the 4 steps, and identify the errors, redo the exercise and come back to the assignment stage and again compare with the actual field observed traffic volume. Repeat the process until there is a reasonable match between your assigned traffic and actual field observed traffic, right. So, with this we complete our discussion on route assignment. All the 4 analytical steps are completed at this stage. To summarize what we have done today, we discussed about 3 assignment techniques, namely all or nothing assignment technique, multipath assignment technique and capacity restraint assignment technique. We have seen numerical examples to understand all or nothing assignment technique as well as multipath assignment technique clearly, and we also know now the capacity restraint procedure is an input for actually assigning traffic either by all or nothing assignment technique or multipath assignment technique. And taking case study as example, we have seen how capacity restraint technique can be incorporated in all or nothing assignment procedure as well as multipath assignment procedure. And finally, we try to understand the difference between assignment of personal vehicle involved traffic and assignment of transit trips. In the case of transit, it is again assignment of person trips into transit service, and other associated problems are related to accurate estimation of travel time and possibility of choices between transit service. All those things are to be considered while assigning transit trips, right. We will stop here and continue with the next topic in the next class.